What we are about now is to come out with a derivation of the expression of the electric potential at a point electric potential. So first let us start with the official definition of the electric potential. So here we go, electric potential. Electric potential is defined. Electric potential at a point is the work done in bringing a unit positive charge from infinity to that point. How do we start with this? We consider that we have a positive charge Q here. So that's Q. I am going to find the electric potential at a point here. Let's call it point A. And according to the definition, the positive charge is brought from infinity, that is from far away. Okay, now to bring this positive charge from infinity, we will drag it along from infinity to point A like this, where it will have at a point A, it will have a voltage VA. And this is what we are about to find. Okay, now to drag this electric charge, we need to exert a force F along this distance, which is R. Okay, the whole distance. Since F is a changing force, so I can't just say that the work done is just F times R, because F is a changing force. So what we need to do is to say that the work done is equal, or part of the work, we take part of the work is equal to force times part of the distance. Taking a small amount of work with a small amount of distance, because we considered that along or during this small distance the force can be considered to be constant, so I can just say work is equal to force times dr. Okay, and we don't forget that the force here is acting in an opposite way to the electric field, which is directed that way, and this way the work done is going to be taken negative. Okay, so part of work, which is dW, is equal to F minus F times dr. Okay, now the next step is that we integrate the integral of dW is equal to integral of negative F dr. Okay, let's see. Let's plug this up. Okay, integral of negative f dr is to be done from infinity, because I'm coming from infinity to a point A. The integral of dw is just w. Now dragging the minus to the outside, integral from negative infinity to A, which is equal. We remember that F is equal in this case to Q. Of course, we don't forget K over R squared dr. Okay, now dragging to the outside the K, Q, and Q, because they are constant, so we get minus K QQ integral infinity to A of dr over R squared, and therefore W is equal to minus, so هيصير عندي K QQ over negative R. okay, which is equal to KQQ over R. Remembering that K is 1 over 4 pi epsilon node, so we have 4 pi 1 over 4 pi epsilon node Q over R. So far this is the work done. Again, I say dragging the positive charge from infinity to point A around the electric charge, the major electric charge Q. Now, according to the definition, we have defined that the electric potential at a point A is the work done in bringing a unit positive charge, which means that it is the work done per unit charge, So from the definition, I can say that the voltage is equal to the work per charge. And according to the conclusion that we got up there, we say that this means that V is equal to what? Dividing this expression, you see this expression, which is W, dividing it by Q, we get that V is equal to 1 over 4 pi epsilon naught Q over R. And that's it. This is the expression of the electric potential at a point. So if the distance between the electric charge that we had at the beginning and the point A, if A is at a distance R from the center of the major charge, so we say that the potential of A is what is a spherical surface around the major charge and at a radius R, a spherical surface of radius R. At any point on this surface, at any point on this spherical surface, the potential is going to be VA, which is equal to, according to what we got here, is equal to Q over 4 pi epsilon naught RA. Of course, remember that the unit is, SI unit here is the volt. Okay. SI unit for the electric potential at any point. According to what I'm saying, since at any point on the spherical surface the potential will be VA, this means that the potential, for example, at this point A is the same as the potential at this point, let's say point B, for example. So if sometimes we needed to find the potential difference between A and B or B and A, it's going to be 0, since they are lying, as we see, on the same potential level. Okay, thank you.